Good afternoon, everyone. This session is on scaling BGP. RST 3321. My name is Luc de Geen. I'm a technical leader in services from the Brussels office. To be more precise, I'm a escalation engineer in the TAC in Brussels. So we have 90 minutes scheduled. Thank you for showing up this late in the day. This is the agenda for today. I won't go over every bullet, but we'll start with introduction and the goal setting. We'll have a look at some memory utilization, full mesh IBGP update groups, quite a bit of MPLS VPN, and we'll round it off with some operating system enhancements. There's only a few hidden slides. I think they will be in the download as well. I just checked. It's not available yet, but it should be very soon, I hope, so that you can download the slides. And at the very end, there's an appendix, just for your reference. What I would like you not to say in the future is we're going to need a bigger boat, right? It's a famous quote from a movie, Jaws. It's when they go hunting for the big shark, right, Jaws, on a boat, and the guy sees for the first time the shark up close and says, we're going to need a bigger boat, instead of saying it's a big shark. But what I would like you not to say in the future is we're going to need a bigger router, right, more performance or more memory, for example. So we're going to talk about design and solutions to avoid you having to say that in the future. What we will not talk about is just pure scaling numbers. This router is this big, has this CPU, can carry this many BGP prefixes in the routing table, and so on and so on, right? It would be, well, we could fill the whole session with that, plus it would be pretty boring. So we're not going to do that. We're mainly going to talk about features, design, and solutions for scaling. So what are some of the scale challenges? Well, first of all, BGP is hugely successful. Everybody's using it in enterprise networks, in service provider networks, and now even more and more in data centers. So it's hugely popular. More and more features have been added. More and more solutions can be done with BGP, right? So everybody is starting to use it in places where it was not used before. Scaling is getting more and more. We see bigger and bigger networks, and BGP is more and more used, even sometimes as a kind of an IGP. Think of data centers. Some of the solutions there actually are using BGP, eBGP, external BGP even, as an IGP. And we'll talk a little bit about more multipath and more resilience there that also have an impact, that has an impact on scaling. If you would look at the internet, you can see that there's a steady growth of BGP. Well, more than steady, it's a little bit exponential. We see more and more autonomous system numbers being used, more and more IPv4 prefixes that we have run out of recently. So that's why BGP for IPv6 is on the rise, right? There, the table is growing really exponentially, because that's the kind of prefixes that we are assigning today. So a lot of growth just by looking at the internet, what's going on there for BGP. So since the beginning, from the origin in 1990, BGP was a solution for inter-domain routing, IDR. Immediately it was very popular, at the beginning just for IPv4. Later on we added IPv6, multicast, all kinds of MPLS VPN stuff. So we see more and more services, more solutions depend on BGP, and hence also more and more address families that we'll see on the next slide actually. But besides that, also the scaling is increasing. BGP, for example, is being used in DMVPN solutions, that's enterprise networks. You see more and more inter-AS MPLS VPN, and unified MPLS, for example, where the network of an enterprise has grown so big that BGP has introduced just to do the scaling. So that's unified MPLS or seamless MPLS. All of these new solutions or features translate into new address families. I'm pretty sure most of you have seen address families under the router BGP configuration. Each address family is a service. So we started off with IPv4, IPv6 was added, multicast, VPNs, and so on. In the end, we end up with all these address families, both in iOS and iOS XR. By the way, everything I say relates to iOS and iOS XR, not so much NXOS, but it could be. If not, in the top right corner, it will just say iOS or iOS XR if it's only for that operating system. So we have bucket loads of address families right now. So a lot of solutions depend on BGP. So let's get started. Let's first have a look at memory utilization. BGP, guess what? Lots of prefixes. It needs to use a lot of RAM. There are three things important when you look at BGP. The number of prefixes, the number of paths, and the number of attributes. Those three things influence the memory utilization. But what can you do about it? Well, when you look at prefixes, there's only three things that you can do, is either aggregate or summarize prefixes. So make sure you have a shorter mask, you have less prefixes. That's easier said than done, right? That's a big change on your design. You have to have contiguous IP addressing and so on. Easy said, not so easy to do it in practice. And filtering prefixes, sometimes in parts of the network you don't need all the routes from the routing table, all the prefixes. So you could filter them out with route maps and so on. Or you could implement partial routing in specific areas of your network. That's possible as well. So that's filtering, and that's basically the only thing you can do. But it can have a huge impact. The number of paths, that's really, you can have prefixes in BGP. The paths is just from how many neighbors you learn that prefix. If you learn the same prefix from 10 neighbors, you will have 10 paths. So how to reduce the number of paths? Reduce the number of peers. That's basically it. And we'll spend quite a bit of time there when we look at the full mesh of iBGP on how to do that. And finally, the number of attributes. Attributes are necessary for BGP. They're used for policy. BGP has a lot of policy, so we need them there. Some of them are needed by specific features, so you cannot remove them. They're needed by the feature. If you remove it, the feature wouldn't work. Other ones are basically just needed for policy. Those are the communities. And those, I think the pointer died. And he's not here anymore. Okay, manual. No, it's the right. It was escape. So you could filter or try to filter out those communities that are used for policies. Again, easier said than done. Once they are there, and they're likely to stay there. I know customers, they add attributes, communities, policies, they never delete something, right? Often you ask somebody, why is that community there? I don't know, but it's been there forever and they must have some use. So nobody will dare to remove it. So actually that one slide is, when you just talk about scaling, is really, really important. It has a huge impact. But none of these things, except maybe the middle one, are always easy to deploy. Another thing that has an impact on memory utilization is soft reconfiguration inbound versus route refresh. Now, soft reconfiguration inbound has been around almost from the beginning of BGP. And it serves really only one purpose. If somebody changes the inbound policy, then how to get the prefixes back on that router, right? Well, the old way we did it was we stored all the prefixes, all the paths and so on, in a raw table before the filtering. So if you change the inbound filtering, we just took all the prefixes again from that raw table, pre-filtered table, put them through the filter, and then stored the result after the filter into the BGP table. Excellent, but we use up more than twice the memory because we have the BGP table and the table pre-filtering. So memory-wise, pretty bad. So we came up many years ago with a solution which is route refresh. Instead of storing the routes pre-filter, when you change the inbound policy, a route refresh request is sent out asking the neighboring router, the peer, BGP speaker, hey, send me all your routes. And it goes through the filter again, and we rebuild the BGP table. Which, by the way, the route refresh is enabled by default, right? But some people, for some reason, they still swear by this solution, right? Even though some of them do not know why. There's only one reason why you would do that. That is if you are doing eBGP with your neighboring autonomous system number, whoever that might be, and you want to see what they send you before you filter them out, the prefixes. Right? That's the reason why some people are still using that. Otherwise, please don't use soft reconfiguration inbound. Memory eater. All right, full mesh iBGP. According to the standard, when you're doing iBGP, all your routers must be in a full mesh. So every router has an iBGP session to every other router in the same autonomous system number. That's the specification. Soon after, they realized, well, that's a big disadvantage, right? So what does it mean? It means if you have n routers, that the number of sessions, BGP sessions in your network is n times n-1 divided by 2. I'm sure you have seen that before. But that's a lot of sessions, right? Now, even though per router, that's only n-1 number of sessions, but that can still be huge. We have seen a few networks where there's a huge amount of iBGP neighbors, meaning thousands. Then n-1 is a whole lot as well. So that poses a scaling problem. What is the solution there? Well, a long time ago, we came up with two solutions. That is configurations and route deflectors. Okay. Both work really well. Both are still supported. Even though the route deflectors is what you see more than 95% of the time, right? And at the end, there's a summary slide for this that will hopefully tell you why that is, why one is more popular than the other. First of all, configuration. What is it? Well, it's really divide and conquer. You will have your autonomous system number. You divide it up in smaller autonomous system numbers. We call them sub-ASs. The bigger AS is the configuration. To the outside world, that's still one AS, no issue. Inside your network, you have smaller sub-ASs. Now, inside one sub-AS, you still need the full mesh of iBGP. But between sub-ASs, you have eBGP. Now, it's configuration eBGP, but technically it's eBGP. And you can set up those green peerings, the eBGP ones, as you want to. You do not have to connect every router with every other router in the other sub-AS. So for example, router 6 does not have an eBGP session with router 3. Right? So full mesh iBGP is only inside one sub-AS, and you don't need a full mesh of eBGP inside the configuration. So this enhances the scalability a lot, right? Plus added bonus, you don't really have to run one IGP here in your configuration. You could do one IGP per sub-AS, right? If you don't redistribute, fine, but then you have to do next hop self to make sure that the forwarding of the packets works, of course. So that's configuration. Works really well. We still support it. Some people think the support will go out. No, we still support it. However, it works well if you deploy either a new network, you start from scratch, easy to deploy, or you are merging two companies. And then maybe the two companies are each one sub-AS, and you make it into one configuration. Right? But if you have to start with an existing network and start moving routers from an existing autonomous system number into a sub-AS inside the configuration, that's a big pain. So deployment-wise, it's not so easy. Right? Change manageability. Route reflectors, that's the second solution. Like I said, more than 95% of the people do route reflectors. And there's a good reason for that. It's easier to deploy for sure. But what is it? We have a special router. It's always in red here, a route reflector, which, as the name implies, reflects IBGP route. So it will get an IBGP route from a neighbor, which we call the route reflector client, and reflect it back to the other route reflector clients. The result of that is that we no longer need a full mesh of IBGP, but we can have a hub and spoke topology, IBGP-wise. So the route reflector is the hub, and the route reflector clients are the spokes, right? So client could get away with one session to one route reflector instead of a session to each other router in the autonomous system number. Right. And then it's up to you if you want to have a full mesh between the route reflector clients or not. That's a choice. So that's a route reflector client. It's much more powerful because a lot is possible. With route reflectors, as you can see here, we can group them into clusters. A route reflector with clients. Each router here can have an eBGP session. The route reflector client can have one, the route reflector, or a router which is neither one, which is just a normal IBGP speaker, a non-client. Each of them can have an eBGP session. One thing to be careful of is that at the top, so here, all the route reflectors, the non-clients, they still need to be in a full mesh. What is a cluster? Well, it's a collection of route reflectors with their route reflector clients. So for example, this is one cluster and this is one cluster. And you do that by configuration. Right. On the next slide, we'll see if that's advantage, if there's an advantage or not. Right. And a client, by the way, in a cluster can still be a route reflector client of a route reflector in another cluster as well. That's perfectly possible. So it's a very flexible solution. Also, what route reflectors can do is we can have hierarchy. We can have different levels or layers there. So we start off with a route reflector client with, a route reflector with route reflector clients. That's one layer. Now those clients, in turn, can also be route reflectors and can have their own clients, right? And so on. So we can build different layers. We have 3 tiers or 3 layers here. So that gives you an enormous amount of scalability. For example, the bottom ones could be the PE routers. They would have their route reflectors in a particular region, and then we could have inter-region route reflectors. Still, at the top, you need all the route reflectors and the non-clients in a full mesh. You can't get rid of that. Back to the cluster. So a question we hear a lot is, when I have route reflectors, what should I do? If I have a pair of route reflectors who connect to the same clients, should they be in the same cluster ID, same cluster, or not? It matters, but maybe not to you. So what is the difference? Let's have an example. Let's say they're in the same cluster. You configure them to be in the same cluster, which is 32 bits. It's an IP address, the cluster ID. And we have route reflector client 2 sending a route. Now, the prefix is sent from one route reflector to the other, but it will be dropped by this route reflector because it has the same cluster ID as route reflector 2, and the cluster ID is inside the BGP message. So it will be sent but then dropped. And by the way, in red here, those are the iBGP sessions, right? Now, some people seem to think, well, that's bad, because imagine that this link goes down, then this router reflector 1 doesn't know the path anymore from client number 2. That's not really true. These are TCP sessions. So even if these were also physical links, if this physical link would go down, this iBGP session, on top of TCP, of course, would reroute over that path, right? So iBGP sessions don't usually go down that quickly unless the whole router goes down. Now, if you would have different cluster IDs, then this route reflector 1 would accept the prefix from route reflector 2 and store it as well. So there's a little bit of extra redundancy in that case, but there's also a little bit more CPU and memory consumed. More interesting question about route reflectors. How many, where to put them, and which kind? How many? It's pretty simple. You need redundancy, so you will need at least 2. Now, here again, we will have the principle of divide and conquer. If you really have a huge network or you have a lot of services, IPv4, IPv6, VPN-v4, VPN-v6, multicast, L2VPN, and so on, then you might distribute different services, address families, over different set of route reflectors, right? So you could have multiple sets. But in each set, you should have at least 2 route reflectors. I think that makes sense for redundancy purposes. Where? Well, not at the same place. That's pretty easy. They need to be in different geographical places, or different data centers, for example, or different regions, hopefully, right? So if one site goes down or is isolated somehow, you still have backup route reflectors. Because if all your route reflectors goes down, BGP is down, right? And then your forwarding is gone. So that's not what we want. Third question is which kind? 10 years ago, that question was very easy to answer, 7200. That's the route, move on. And we still see that router being used a lot for a route reflector. Why? Well, a route reflector, what does it do? It reflects BGP routes. It needs to learn the BGP next hop, so it also needs to run IGP, okay? That's BGP, IGP, what else? Nothing else. It doesn't need to forward packets. It could, but it doesn't have to. And it doesn't need to run MPLS or multicast and so on and so on. So just BGP and IGP. And that's what we call a dedicated route reflector. It just does those 2 things. Can you have another router be a route reflector? Sure, your 7600 PE, GSR, CRS, whatever. It's maybe an MPLS VPN provider edge router or layer 2 VPN router, whatever. Yes, it can be a route reflector as well. Does it make sense? Maybe not, right? So that's a dedicated RR. What does it need, a dedicated RR? Well, it's just about storing BGP prefixes and processing them as quickly as possible. So storage is memory, processing is CPU. That's all what you need. Lots of memory, good CPU. So these days, more popular is the ASR 1K, right? It's small, doesn't consume that much power, but has a good CPU, can have plenty of memory. So that's a good successor to the 7200, sorry. But guess what? What's the buzzword for the last few years around? It's, yes, SDN, NFV, but also virtualization. So we can also virtualize routers, right? And to be honest, if there's one thing that we can, well, one good reason to have a virtual router for, it's the BGP route reflector. Because like I said, dedicated RR does 2 things, BGP and IGP. That's not a lot. Well, that could be a lot, but that's not a lot of things it needs to do. It doesn't need to forward packets, for example. It doesn't need to do 1 million packets per second, right? So Not too much forwarding is needed. So in that case, we could go for a virtual router. And to be honest, that actually makes sense. You can easily deploy a virtual router. It's easy to manage. At the moment, you can suddenly increase the memory when you need to. You can increase the CPU when you need to. Upgrading is easier. You just clone it, upgrade the other one, you test it, and put it in production, and so on and so on. And we kind of have two good products for that. Is either the iOS one or the iOS XR one. The iOS one is the CSR 1000V cloud service router. iOS, very good. Or the ASR 9K-V now, right? Similar, but it's running iOS XR. What about this? What about if you have a dedicated RR? Well, I've seen a lot of those RRs, and a 7200 or an ASR 1K, whatever. They had 1 million routes. And all those routes were put in the routing table, and all those routes were put into the FIB, which is the forwarding in the data plane, right? We call it the CEF table, Cisco Express Forwarding. So in the FIB or CEF table as well. But it's not needed because the BGP router reflector only receives packets and sends out packets. So it's local packets. It doesn't forward packets through the box. So it doesn't need to install all those prefixes in the data plane, into the forwarding plane. So what you could do on a router reflector is just make sure that the BGP routes are not installed in the routing table, and hence also, next step, not installed in the FIB table or the CEF table. And that's what a lot of people do not do. You could do it in iOS and iOS XR, and we do that with a table map in iOS, and in iOS XR with route policy language, RPL, filtering. If you do that, you block all the routes. Routing table is empty of BGP routes. You still have the IGP routes, but that's maximum a few thousand routes. And no prefixes in the forwarding plane, CEF table or FIB table. In iOS XR, similar, but there we use RPL, route policy language. Okay. Why is it so advantageous to do this on a dedicated RR? Well, each time, there's a lot of BGP updates happening, right, all of the time. Prefixes change. Each time the router will have to install it in the routing table and then in the FIB table. And this is quite expensive, especially the last part, putting it in the FIB table and push it out to the hardware. That takes a lot of time and CPU power, but especially time. So it has an impact on convergence. So on a dedicated RR, you can block off all the routers. All the routes, sorry. And by the way, this would only be for address families IPv4, IPv6, not for MPLS, layer 3 VPNs, and so on. Why? Because then the forwarding is MPLS packets anyway. We don't forward through the routing table, which is IP forwarding. Last thing here is multi-cluster ID. Since 2 years in iOS XR and more recently in iOS. What is it? I'm not sure it's being used that much. The idea is here, instead of a route deflector servicing one cluster, it could service multiple clusters. So clients, route deflector clients in different clusters. What's the point? The point is, again, divide and conquer. We have the clients in one cluster and other clients in another cluster. If those clients are iBGP connected, so there's a full mesh between the clients in one cluster, then the route reflector does not need to reflect routes anymore between clients of the same cluster. The P of the route reflector, right? Yes. Oh, here as well. Yes. But yes. It's defined here as well, but we don't, the route reflector does not need to reflect the prefixes anymore. Small gain for route reflector, small loss for the clients. They have to do a little bit more work. Actually, what I did 6 months ago, for a few of these features, I wrote some scripts that goes to all the attachments that you people upload for tag cases. show text, iOS, XR, and so on. And I look for features enabled on the BGP. This one is not very popular. Final slide here on configuration, confederation, and route deflector clients. So the solution for the full mesh iBGP. Both are very good. Both are, we still support, but there are two big differences. Migration-wise, deployment-wise, the route deflector solution is much more easy than the confederation one. Scalability, again, route deflector one is better than the confederation one, mainly because we have the hierarchy in route deflection. Any questions, maybe? Route deflectors, configurations? All right. That's all iBGP. One note on eBGP. Sometimes, that's mainly on the internet, you can see kind of a full mesh of eBGP sessions. And that's what happens at the internet exchange points, where the service providers interconnect. They have an eBGP session from their router to every other router, from the other autonomous system numbers that come together there, right? So at different places in the world, we have these internet exchanging points. So it's kind of full mesh, but now for eBGP. But manageability, again, here can be cumbersome, because if you add a service provider, he will now have to create a session, eBGP-wise, to every other router, and all these routers will have to create a new session to the new service provider connecting there. Right? So the solution there for eBGP is what we call route server. And it's very similar like a route deflector for iBGP, but now for eBGP. Two things. We insert a router here that will reflect the eBGP routes. But one, the AS number doesn't appear in the AS path, right? So this phony AS number 999 here will not appear in any of the prefixes that are going through that exchange point. Second, this box, router 5, AS999, it doesn't do next hop south for a very simple reason. If you would do it, then all the traffic would actually go through that router of the whole exchange point. And maybe it will not cope with that. So no next hop south here for BGP. That means if traffic comes in, for example, from router 1, needs to go to router 2, AS200, it will go directly there. This is typically a VLAN somewhere, right, in a building. This is just for your information. This is the configuration that we have for route server in iOS. All right, enough of the full mesh. Update groups. Oh, one question. On this router? By default it will. I think you still have to do this RIP filter, this table map. Yeah. The routes will be there, yeah. But the packets will not go through the router, right? Yeah. Okay. Update groups. Who thinks? Question? Using what? Two connectors? Which one will be faster? Root server or route deflector? I think it's more or less the same, but it's kind of a question maybe we should not ask, because one is for a solution for eBGP, root server, and route deflection is a solution for iBGP. So why compare the two, right? You can use route reflectors only for iBGP and route server only for eBGP. So does it matter if one is faster than the other? I don't know. In principle, they should be more or less equally fast, which is probably not fast enough for most people. So you need other features to make sure that fast convergence is really fast in the milliseconds, right? It's probably not that fast. So, but we'll have a section on that on fast convergence, by the way. I have a question. Who knows what update groups are? Oh, is now somebody afraid that I will pick you out? Can you define update groups, maybe? Or try to?
You define an update group. All the updates that you send are the same to all the routers in the same update group.
That's good. That's perfect. So all the updates that you send are the same. So you imply that the updates you send on other update groups are different, right? I was hoping that somebody would say, yeah, that's peer group, whatever. Not exactly. Let's have a look what they are. So we are talking about optimization. On the one hand, optimizing the CLI is reducing the amount of stuff you have to type. That's really peer groups. That's about templates, session groups, and so on. That's CLI only. I know in the past, peer groups was kind of synonymous as update groups. They kind of did the same thing. But, I don't know, 12 years ago, something like that, it was split up. Peer groups is CLI only. Update groups is what we really care about because that gives you the performance scalability, nothing to do with CLI. In fact, you don't see it in CLI. Update groups are a dynamic way where we group sessions, peers, BGP peers together. How? By looking at the outbound policy. We say, hey, this set of BGP speakers, they have the same outbound policy from me to them. Those BGP routers, they have a different set of outbound policy. We group them together. Why? Because when I need to send an update to that group, it'll be the same update, BGP message. They have the same outbound policy. That group, again, it will be the same update that I send to those routers. So it's per outbound policy. That's very important. It's dynamic. We take care of it for you. The router does it, of course. There's no CLI you can, well, except for one thing, but there's no CLI that you can type to enable it and so on. And it's per address family. So you can have an update group for IPv4 address family, one for the IPv6 address family, and so on. It's enabled by default. So it's there on your BGP router. You cannot disable it, so it's there. Maybe you do not know about it, but it is there. Did I escape again? So outbound policy, that can be for iBGP sessions and for eBGP sessions. But where does it matter the most? Well, guess what? A route reflector, one, has a lot of clients, a lot of sessions. Two, on iBGP, you do not usually fiddle with the policy, specifically not on a route reflector. You don't change the outbound policy. You shouldn't if you do, but normally people do not, right? So there, all the clients typically have the same, or the route reflector has the same outbound policy to all those clients. So that's where we can definitely use update groups. And so let's say you have a route reflector with 101 clients. All those 101 clients will be in one update group. So if you do show BGP, whatever address family update group, you see how many members that you have there. And this is, of course, both in iOS and iOS XR. Why is it so good? Because we found out that a lot of the CPU needed by BGP is about creating a message. Not sending it, but creating each time the BGP message. So without update group, we would have to create and send a message for each peer. Now with update groups, we create a message for one of those routers in the update group once, and then just replicate it. And it goes a lot faster in the code. So there's a big benefit there. So basically, again, a route reflector could be any router, right? Update groups are all over the place, iBGP, eBGP, P routers, and so on. But in a route reflector, typically we have the most neighbors. So there we'll gain the most benefit. So, and also we have the same outbound policy, namely no outbound policy. So we update, we format one BGP message and we replicate it for all the neighbors. So if you have n neighbors, we replicate it n times. Can you see that on your routers? Yes, there's a command in iOS and iOS XR to actually track the update groups and how efficient the replication is, how fast we are sending them, and so on. This is an output from iOS. Show BGP address family, replication, and then the update group number. You see how many neighbors we have there, 101 BGP neighbors. How many messages we formatted, replicated, and what is the cache size? The cache size is a queue. We build a BGP update message, or withdraw. We put it into the queue, and then it's sent off to all the neighbors, right? Here, the queue size is 2,000. So very powerful, but it's enabled by default. You cannot turn it off, so no need to worry about it. One thing we did in iOS at least is change this cache size. It used to be fixed, and then we figured out, well, do we really need a cache size of 2,000 for all the address families? That big, and does it need to be the same everywhere? No. So we made it kind of adaptive. Depending on the kind of router, how much memory you have, which address family the update group is for, how many neighbors are in that update group, we make it a little bit variable, the queue size. And it goes from 100 to 5,000, right? Yeah. Question? Okay. Filter groups. Yeah. 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 Can I come back to that because I have a slide on that? The question was on filter groups. And that's more specific for iOS XR. Yeah. I'll come back to that. All right. Route refresh. Remember soft reconfiguration inbound? Route refresh. I send a request to my neighbor, and he should send a route refresh request. He should send all the prefixes to me, right? This can have an impact on the update group, because if you have one router that constantly sends a route refresh request, I have to send always my whole update, but it slows down the sending of updates to the other update group members a bit. So what we did there, both in iOS, but slightly different than in iOS XR, we can kind of process it in parallel. So we can do the full route refresh update for the router that sent the route refresh request, while at the same time we continue updating the transient updates. So sending the transient updates to the other update group members. All right. So again, something that we did in the background inside the code. The only time you would see it is in iOS if you have these flags set on the BGP prefixes, or in iOS XR when a route goes from an update group into a refresh subgroup. And once it's done, the refresh update, once it receives all the routes, it will go back to an update group. So already, to partially answer that question about filter group, in iOS XR, we kind of chain the way we work with update groups. So we have an address family, IPv4, and then we have the different update groups. Then we can have subgroups, which are, for example, a refresh subgroup, which I just explained. And then we can have filter groups, neighbors, and maybe other groups as well. So it's a chain of how to organize these update groups. Refresh subgroups we just saw. Filter groups will come back with route target constraint. So this is just an output in iOS XR. By the way, you can have many update groups, right? If you have 10 kinds of outbound policy, then you will have 10 update groups. There's no limit to that. Update groups helped a lot. It helped scaling BGP a lot, right? We have to send, or we have to consume less CPU on the route deflector, for example. There's, however, one problem that still occurred is, what if you have a slow peer? What if you have an update group and you have one or two guys which are a bit slow and they drag the other guys, behind? So for example, here in this update group, you might have two peers which are slow. That could be for any reason. The CPU could be hogged at 100%. They could be running out of memory. The BGP updates in between the router reflector and the router could be dropped. So we constantly have to resend the BGP message over TCP and so on. So the reason could be anything, right? But we now have a feature in iOS where we can automatically detect that we have a slow peer. It's not enabled by default, so you have to enable it. If you enable it, then we will have a syslog message on the router reflector saying for that update group 1, we have 1 or 2, whatever, slow peers. And they will be moved out of the update group and be put into a special update group for slow peers, badly behaving BGP neighbors. They will remain there as long as they're slow. Right? And then there's a choice. Either you go in there manually, you have to type something on the CLI, and then that slow peer, if you think it's not slow anymore, can go back to the original update group. Or you can enable the automatic protection, not protection recovery, meaning that once the router says, the router reflector, these routers are no longer slow, he will then move them back to the original update group. So that's slow peer. It's in iOS, not enabled by default, but you can enable it. And it makes a lot of difference in the convergence time if you have routers which are slow. That's a feature in iOS, has been there quite a bit. 5, 6, 7 years, something like that. Okay. So what about the CLI? That's for iOS. The detection, yes, you can enable it per address family, per VRF, and so on, per peer group. Protection meaning, how do you move the slow peers? Either statically, it means once you think there's a slow peer or you get a syslog message, you have to type a command and move that 1 or 2 peers out of the update group. You have to type the command. Or it's dynamic, that you enable. That means when the router reflector in our case thinks there's a slow peer, after a while, it doesn't, by the way, the detection is not too fast, right? We don't say after 1 second, this peer is slow, we move it out. After 2 seconds, oh, it's not slow anymore, we move it back. No, it's in the order of minutes, right? So after a few minutes, after being slow, the router will move it out of the update group. And one of the main things the router will keep track of is the queue size that we talked about. If the queue size is constantly filled up with BGP messages for the update group, then we have at least 1 slow peer. Right? Then it's a matter of detecting which peer it is and moving it out. You can do it manually, or dynamically the router will do it for you. And then the other option is permanent or not. Permanent means once the router is slow, it will stay slow forever in the special update group for slow peers until you move it back manually. If you don't put permanent, then the router, hopefully, at some point in time will say this or this peer is no longer slow, and he will move them back to the original update group. Okay. And finally, there are some show commands for BGP which have been enhanced with slow at the end to track what the slow peer feature is doing. And also there's a clear command. The clear command moves the slow peers back into their original update group. What did people do before this feature? Or what can you still do if you have a router without a slow peer feature? Well, do it the old way. Remember what an update group is? Peers, neighbors with the same outbound policy. So the only thing that you need to do to make, if you detect a slow peer and you want it to move out of the update group, is just give it a different outbound policy. Hold on a second. I mean, policies, playing around with policies in your network is probably not a good idea. So don't change the local preference and things like that, right? No. Go for something easier, is the MRIA. So the minimum route advertisement interval is the minimum amount of, typically seconds, between consecutive updates to the same peer for a BGP update, right? It's either 0 seconds typically or sometimes 30 seconds. What you can do is, if you detect a slow peer and you want to move it out manually, just bump the timer with 1 second, right? Increase it or decrease it with 1 second. So it has a different outbound policy than all the other peers, and that router will be moved out. That 1 second, it won't make a difference on your network. Okay. This is for your information. How would you detect a slow peer? You basically use the command show BGP address family whatever update group. You look at your main routing table version, the table version for the neighbors, and see if it's always lagging behind. Table version, what is it used for? It's used to track which prefixes that still need to be sent to which peer, right? That's what we use table version for. So if it's always behind, that means the whole update group is slow. Why? Well, probably there's 1 or 2 peers which is slow. If you look at the output queue, you will find which one is slow. It's always at the maximum. And this is just another way to look at it with show BGP, the replication command that we saw before. Okay. Any questions on slow peer? Yes? Yeah. No. So what about XR? We don't really have slow peer detection. I think it might be coming. No, that's what I can say. But we don't have it. So yeah, either you do it manually or nothing. Yeah. So I did say it's only for iOS, right? Route reflector problems and solutions. So route reflectors are great. It solves the full mesh. Guess what? Everything has a disadvantage. It also imposes us with problems. Let's say you have a network, iBGP, you put a route reflector in there. What does it do? Well, it hides some information. Let's say you have an MPLS VPN network, but it can be plain IPv4 network as well. Your egress routers, they advertise a prefix Z. The route reflector, what does it do? It sees multiple paths for the same prefix, does best path calculations, all 16 steps, picks the best one, and advertises only the best one. That's per the BGP standard, period. That's what all the BGP speakers do. Great, but now this router, for that prefix Z, only sees one path with PE1 as a next hop, not PE2. So what's the consequence? Well, now PE3 cannot do certain things anymore. Like what? Cannot do load balancing, because it only has one path. It cannot do fast convergence. It will converge from one next hop, PE1 to PE2 for sure, but in the order of seconds. It doesn't have the second pass with PE2 as a next hop ready, right? Because if it would have the second pass before the failure, it could quickly switch over. Now it will have to wait until the failure happens, then BGP sends a new update, and so on and so on. So this takes a bit of time. The other thing it cannot do is hot potato routing, but we come back to that. And finally, this is really obscure, but I've seen it twice or 3 times at my years at Cisco. The tag is prevent oscillation with MET. Now, if you want to know what that is, it's really a corner case. There's an RFC actually describing that specific corner case. And there's not much you can do about it except play around with policy and so on. But sometimes, you know, you need multiple paths to prevent that corner case. Anyway, we want the router to learn more than one path. So that's a problem with the route reflector. It will only send one path. So there's a few solutions here. Now, if you run MPLS VPN, a solution is related to that is to have different route distinguisher for the same VRF. And then we have some other solutions that we will go through now. Unique RD, if you have MPLS VPN, this is by far the best solution. A prefix is advertised, from the different PE routers, but with a different route distinguisher. If you know how VPN v4, v6 prefixes work, the route distinguisher is part of the prefix. If the route distinguisher is different for the same IPv4/v6 prefix, then it's a different prefix. So the route reflector really sees two different prefixes, so he advertises them both. Problem solved, but only for MPLS VPN, not for IPv4 or plain IPv6. Another feature is what we call shadow route reflector. You have a route reflector, RR1 there. It learns the prefix from the two paths, P1 and P2, picks the best one, advertises only the best one. Now we introduce a second route reflector, which will kind of do the opposite. It does best path calculation, but it will not advertise the best one, but the second best one. Why? Because you tell that router to do that with the diverse paths backup command. On this slide, it's a different physical box. On the next slide, it's the same, right? Because the disadvantages here is what? It's an extra box. It costs money, right? So, do you want to do that? It's definitely a different router. It's a shadow route reflector. Actually, the next slide. First, be careful. Sometimes it just, you might implement it and it doesn't work. Why not? Well, if the route reflectors are co-located, like you have here, they're in the same place, so they're likely to be at the same distance of the remote PE routers, IGP distance. Then when they do the best path calculation, they end up with the same best path, the one with P1 as the next hop, and then it works, the shadow route reflector solution. In this case, it will not work. Why not? Well, route reflector 1 still picks PE1 as the next hop for the best path, but the shadow route reflector is now closer to this box than he is to this box if all the links have the same IGP cost, right? This is cost 1 hop, this is 2 hops. So route reflector 2 picks P2 as the next hop for the best path. What will the shadow route reflector do? Advertise the second best path, which is this one. So now the route reflector 1 and 2, they advertise the same prefix. So it doesn't work anymore because they're at a different distance. Remember, when you look at BGP best path calculation, IGP cost is step 8. So that will be the one here that makes the difference in the best path calculation. Can you solve it? Yes. We introduced a new command, that one, to ignore step 8 in the best path calculation, the IGP one. So we don't care the cost from the route reflector to the PE route. We don't care. Okay. And then they will pick the same best path and the feature works again. Coming back to your question, do we need really a different router, an extra route reflector? Not really. Look at that route reflector. We know what it does. It advertises the best path. What if you would have a second session? And over that second session, we use this trick of diverse path. That will work. Then over this session, it will advertise his second best path, the one with P2 as the next hop. And again, on P3, we have both paths. The only thing you need to be careful of is that the second session is between different loopbacks, so different peering points than the first session. The same will not work. I tried that. Does not work. Pick prefix independent convergence. Who knows what that is? That's minority. So very quickly, when changing from one next hop to the other, that can take time. And what we did for a long time is what we call here the flat FIP. We change the prefixes from one path to the other, from one next hop to the other, one by one. It takes an enormous amount of time, many seconds. Some platforms, minutes, it used to be. So our solution is make sure the backup path, so the second next hop, is ready in the data plane to be used immediately. That's one. 2, switch all the prefixes from one path to the next path in one shot, all at the same time. In software, that's just a pointer we move. Somehow we didn't do that for a very, very long time. Right? That will highly increase the convergence. Now, for that to work, why do I mention it here? For that to work, we need a backup path ready before the failure, so we need to have more than one path. So in this case, let's say it's an MPLS VPN network, full mesh IBGP, P3 for prefix Z has two paths, P1 and P2 as a next step, two paths. We don't have this prefix-independent convergence, so what will happen? When one router goes down, through IGP, PE3 learns pretty quickly that the router is down. Then we'll do BGP best path calculation, update routing table, BGP table, push the routes into the hardware. This takes many, many seconds, usually. It's pretty slow. So that's no prefix-independent convergence. Now, if you introduce prefix-independent convergence, for example, by this command in iOS, but iOS XR has it as well, if you have a full mesh, then the second path for the same prefix will be installed as a backup path in the routing table, in the FIP table, in the hardware, the TCAMs and so on. So now when the egress PE goes down, PE3 learns about it reasonably quickly through the IGP updates. Doesn't do best path calculation and switches all the prefixes from primary next hop, which is down now, to the backup next hop, all at the same time. Prefix independent convergence. So we eliminate scanning BGP table, best path calculation, updating the FIP. And that saves a lot of time, specifically the last one, updating the FIP, pushing the FIP from the RSP, for example, to the line cards. That takes a lot of time. Now, be careful because sometimes it doesn't work. If you have a full mesh with default policy, then this prefix Z will be advertised by both PE routers to PE3. PE3 will have two routes, two paths for the same prefix, and you can do this prefix independent convergence things, the PIG thing, no problem. But that's default policies. What if you fiddle with the policies? For example, and that's typically what happens, you want to have P1 to be the primary router and P2 to be the backup router, right? So you increase the local preference from 100, the default to 200 on P1, so it tracks all the traffic. Great, will work. But now P2 will also pick the path with P1 as a next hop as the best path. And he no longer advertises himself or the path through himself to the other routers. So P3 only has the path from P1 and no longer the path through P2. You cannot do multipath, you cannot do PIC on P3, nothing. So what's the solution here? The solution we came up there is best external. Again, route advertising like before, but now if you enable best external on P2, it will pick next to the best path, which is the one from P1, also the best external one. So external is eBGP between CE1 and P2. It will pick that one as a best external one, will mark it, and then advertise that to P3. So now P3 again has two paths. One on P1, through P1, one through P2. And you can do pick again. Final solution. So the route reflector is a great solution. It does introduce some problems. Final solution is add path. Add stands for additional paths. So now we will have the route reflector advertise additional paths. Not just one, the best one, but more than one. You have to enable this feature. Now the route reflector, besides the best one, it will also advertise additional paths. For example, the second best one, the one from P2, with P2 as a next hop. So now P3, ingress router, again has two paths and can do, for example, PIC or load balancing, multipath. However, note, you need to have the configuration on the route reflector and the PE routers to make that happen. So you need reasonably recent code on the route reflector and the PE routers, otherwise it doesn't work. Yeah? Why? Because imagine that the route reflector is sending updates or withdraws for a prefix. He sends an update for the prefix Z with P1 as the next hop, and then he sends a withdraw for the prefix but with the next hop P2. What is that router supposed to do? What does it mean? Different updates for the same prefix each time? Do I overwrite the update, or is it two different updates? What? So what we had to introduce was we had to change, the packet format of the BGP messages. We had to include something that makes the path for the same prefix unique, and that is called a path identifier. So then PE3, when it gets an update, it can discriminate and say, okay, for the same prefix, this is for the first path or for the second path or an update for the third path and so on. That's why the edge routers, the PE routers, and the route reflector need new code. There's kind of two flavors to this, add paths. Either you do it for all paths. That means the route reflector, for example, will send all paths. If he has 100 neighbors and he learns the prefix from 100 neighbors, he sends all 100 paths. That's a lot. That can be useful for hot potato routing, because for that you need to have all the paths available. Right? Or you can have the route reflector, for example, advertise n paths. Let's say n is 2. What does it mean? The primary path, 1, second, 2, the backup path. That's for the cases when you only need a primary and a backup path. For example, for prefix-independent convergence. Okay. So you kind of have two flavors, and then a special one only for iOS XR is multipath. This is the commands for iOS, and these are the commands for iOS XR. Again, you can use route policy language there to do more specific things. So again, a feature for both for iOS and iOS XR. So hot potato routing, what is it? It's more just for service providers. Hot potato, it's about passing, you get a hot potato, you pass it along as quickly as possible. So you're a transit service provider, you get traffic, you want to get the traffic through your network out as quickly as possible. So you go for the closest exit point, P3. Closest exit point is shortest IGP path. And by default, if you have a full mesh, P4 will learn all the paths. Step 8 in the best path calculation, IGP cost, so it will say, yeah, that's the closest one. Send the traffic to P3. So hot potato routing works. We have a full mesh. Again, we introduce a route reflector, and let's say we introduce it more to the left of the network. That route reflector also does best path calculation. It also does the step 8 IGP cost. Guess what? It's closer to PE1 than to P3. So for the route reflector, the best path is to PE1. So it will advertise only the path to PE1 to PE4. Now the traffic for that transient service or transit service provider will go PE4 to PE1 and no longer the shortest path out. So the solution here is, if it's MPLS VPN, unique RD, or, for example, add paths. Right? Both for MPLS VPN or IPv4/IPv6. Large transits, it's just another example of add paths. In bigger networks, we have a full mesh of route reflectors. If you introduce add paths, then you could put another hierarchy of route reflectors there in the network. In fact, I'd still do hot potato routing if you enable add paths. In fact, if all the border routers, edge routers also support add paths, you could just have one route reflector here directly peering iBGP to all the border routers. Any questions? Yes? Yes, XR, yes. So a question, can you do it per VRF basis? Pick yes. Yeah. Deployment, a couple of notes there. This is really about, maybe you should skip the slide, this is really about, again, if you have a lower end box that still needs to advertise all the prefixes, but doesn't need to, or cannot store all the prefixes, you use this filtering again. So you don't put all the prefixes from BGP table into the routing table and into the FIP. Past MTU discovery. So here are just slides with a couple of small notes. They might have a big impact, but little things. Past MTU discovery. BGP uses TCP. Please make sure that you have path MTU discovery enabled and that it works, so you don't block ICMP messages anywhere, the 3/4, right? Path MTU discovery will work. You'll have big MSSs, maximum segment size for TCP. BGP, instead of sending 3 smaller packets, can send 1 big packet, and it will be much more performant, right? Just something to be mindful of. What does have a big impact on scalability are the session timers. What we would not want you to do is on one router to have 1,000 eBGP sessions, and on each session you configure the minimum timers. 1 second for the keep alive, 3 seconds for the hold time. That doesn't really scale too well, right? That has caused quite a bit of problems where you see a lot of hold timer expired for the BGP sessions without good reason, just because the routers couldn't keep up. What we want you to do is enable BFD, bidirectional forwarding detection. It's especially designed to be fast, right, on all our routers. So you just enable it. Between a pair of routers, we have BFD control packets going back and forth. You could set timers. If, for example, you send a BFD packet every 15 milliseconds, after 3 times of a missed packet, 45 milliseconds, you declare, the routers declare the BFD session to be down. It will notify its clients. Who are the clients? All the routing protocols, including BGP. And then BGP session will go down. What we do not want you, again, do not want you to enable is fast session deactivation. It's a feature whereby in the router, the BGP speaker, tracks the route to the remote loopback that is used by BGP. If the route goes away from the routing table, even for 1 second, the session goes down, right? But it happens a lot in the network that sometimes a route disappears from the routing table 1 second or a few seconds. Now, bringing down the neighbor, that's a big thing. Because bringing it back up, over the BGP session, a lot of BGP messages have to be exchanged. And this can take sometimes minutes if you have a huge BGP table. So that's, a hammer. So don't enable that. By the way, we have a good solution, which is enabled by default, which is next hop tracking. So in the routing table, we track the next hop, the BGP next hop. If that next hop dies, because the router dies, we just forget about those paths and we switch to the other paths that we know about for that prefix without killing the neighborship. Dynamic neighbors, that's really something CLI-wise. You can have configuration. You don't need to specify all your neighbors one by one. If you configure a range and you have a BGP open message coming in from that specific range, you allow the session to come up. That's really saving you time in typing. That's it. Otherwise, no benefit. I think I'm running behind a little bit, so I skip a few slides. Multi-session. Multi-session is an interesting feature, only available in iOS. What is it? Well, typically between a pair of routers, you only have one BGP session, hence one TCP session. A long time ago, we came with a new solution, multi-topology routing. Great. Different topologies, and we'll have one routing protocol or address family per topology. A topology could be equality of service. So you would have a routing protocol running a topology for COS 1 and another topology for COS 2 and so on. Great feature. But none of you used it because nobody is using it, it seems. So it didn't take off. Nevertheless, because of that, we had a feature where BGP has one neighborship, you define one neighborship, but still it can bring up multiple TCP sessions between a pair of routers. We took advantage of that and said, well, now we can have one address family per session. Instead of one topology per session, you can also do one address family per session. Looks like a great idea, and actually it is. Because imagine you enable this multi-session, then you can have one session for IPv4, one session for IPv6, and so on. If you run into a problem, and it's only a problem of IPv6, you can just clear the whole TCP session for IPv6. All your other address families will still be up and running. Not only that, but if tomorrow you enable a new feature which uses a new address family, the address family is just added because a new TCP session is brought up. Great for troubleshooting, great for management, but scalability very bad, because instead of having one session now, if you have 10 address families, you could have up to 10 TCP sessions. Here as well, I created a script 6 months ago to see how many people are using it. This time I was surprised. A few people, customers, are using this feature, which, by the way, is only available for iOS. So this is for your information. This is how it looks like on the routers. Right? And here are the disadvantages and advantages. And the only place where you really want to do something like this is IPv4, IPv6. Because if you have, for example, an IPv6 address family, so IPv6 prefixes, running on top of an IPv4 session, that's not so easy. You have to put in some manually, you have to put in some configuration to change the next hop. Because for IPv6 prefixes, the next hop we expect is IPv4, IPv6, and the other way around. So there you have to put in some configuration. So if you really insist on having different sessions, one for IPv4 and one for IPv6, go ahead, that's fine. Then you have 2 sessions instead of 1. That's still scalable. MPLS VPN, scalability-wise, again with router reflectors, 2 solutions. First one, the oldest one, is divide and conquer again. We will divide the router reflector into group, and we'll have each router reflector group service a particular amount of VPN v4/v6 prefixes. How? By looking at the route targets. Each takes care of a range of route targets. So then route reflectors have less to do. This is an example that I tried once. The blue ones, they just take care of the odd route targets. The red one, route reflectors, take care of the even route targets. Sounded like a good idea. Again, I have a script running. How many people are doing that? I didn't find any. All right, so not very popular. And I can see why. It has some disadvantages. Amongst others, extra routers, extra session. Second solution, much better, is route target constraint. Even in the previous case, the PE router would send all its prefixes to the blue route reflectors, but the blue route reflectors would drop the route VRF, the red VPN prefixes. So a lot of stuff happens there which is not necessary. With route target constraint, we'll have the route reflector only send the routes to the specific PE routers which are wanted. How does it work? Well, first of all, we have capability exchange. It's a new address family, new capability. Beforehand, over this new address family, RT filter, there was a question on that, the PE router says, hey, I'm interested in green and red VRF routes. And he says, I want all the prefixes with these route targets. The route reflector says, I'm a route reflector, I want all the route targets, all the VRF prefixes. So he sends a 00 route target. In the end, the PE router sends all his VPN prefixes to the route reflector. The route reflector looks at this that he stored in the address family, route filter, RT filter, and he sends only red and green prefixes, not the blue prefixes. That saves a lot of CPU. Yes?
So when you enable that scalability, that actually happens automatically, no configuration, right?
No configuration, but there's one command, right, to enable it. Yes. And it enables a new address family. Yes. The rest is automatic. However, if and I'm skipping ahead. If you have a PE router with all the code, it cannot do this route target constraint. The solution is there without using this new address family. So what we are going to do is a hack. We are going to have the legacy PE send a special prefix in a special VRF for those route targets and announce that to the route reflector in VPN v4 address family or v6. And there are special communities there to say, hey, these are the route targets. So we put the route targets inside the communities. Okay. And then there's one command you need to configure on the route reflector so that it knows, hey, that guy is a legacy PE, he wants to do route target constraint, but he can't, so let's do it with this hack. So if you have a legacy PE here, which is PE2, he will send, after you configure this phony VRF with a phony prefix and a phony route target, he will send this prefix with this route distinguisher you configure for this VRF with the red and blue route target. So now the route reflector knows if I send prefixes to this PE, I should only send red and blue VRFs. And this feature is used a lot by customers. This helps a lot. And you don't need extra route reflectors or extra BGP sessions. This is the configuration for your information. Full internet in a VRF, this is popular topic. There's a lot of people doing that these days. Why? It gives a lot of benefit. More flexibility in your design. So all the internet routes, 600,000+ today, IPv4 only, in a VRF. Yes, but it uses up MPLS labels. There's only 1 million MPLS labels. Hard-coded, because 20 bits is about 1 million. So no more than 1 million. It can be used for easy deployment of denial of service attacks and so on. Right. Or just to remove IPv4 from your core routers if you are running MPLS. So that's what more and more people do, but it does put a burden on the memory and bandwidth consumption in your network. Right. Also, if I again look at an MPLS VPN network, if you are a service provider or a customer of service providers, for redundancy, you probably have peering into two different neighboring autonomous system numbers. If you have a route deflector and you want to make sure all the remote PE routers know about the two paths, you would have to configure the route distinguisher twice. But that means all the prefixes will be advertised twice, stored twice, and the MPLS labels, well, you have extra MPLS labels consumed. And by the way, if you use add path, that doesn't really solve the issue. So be careful there, okay? By the way, still on all our boxes, iOS and iOS XR, we always have per prefix label allocation. Every prefix in a VPN, v4 or v6, always has its unique label. Is it really needed? Sometimes not. You could do, if you want to save on the MPLS labels, you could use per CE label space. That means if those routers advertise prefixes, for a prefix with CE1, any prefix with CE1 as a next hop will have the same label. Any prefix with CE2 as a next hop will have another, but the same label, and so on. So we only have one label per CE next hop. And we still do not do IP lookup on PE1. We just look up the VPN label when forwarding packets. So we are good there as well. Right? So we can save a lot of labels here. Be careful if you have things like eIBGP load balancing or PIC, that might not always work with per CE label. In iOS XR, we fixed that problem with the persistent per CE label, but not yet in iOS. It's a hack in the code. I could explain how it works, but it's just a hack in the code. So you could go even further per VRF label. That means all the prefixes that you learn from one VRF, no matter how many CE routers you have, they all have the same label. So when the router advertises different prefixes, but from one VRF, they all have the same label. Great, one label, all prefixes. However, when the packets come in the other direction, when we do the lookup here, after the label lookup, we still have to do an IP lookup. because we need to know where to forward the packets, to which CE router. And again, some things might not work here. EI-BGP load balancing, you might have micro loops in certain conditions and so on. Right? So that's something to be careful about. Don't forget you have 1 million labels, so most people didn't hit that limit yet, right? That should be obvious. Even if you put the whole internet routing table inside one VRF, that's still only 600,000 labels. That's a lot, but a little hack, but some things come for free. If you have an iOS XR router, if you have an ASR 9K router, what we enabled for you in the past, so starting from XR 4.2.0, is this feature where we do selective VRF download. We do not download all the VRF routes to all the line cards. We were a little bit careful. We said, well, if a line card only has 3 VRFs, only send the prefixes of that 3 VRFs to the line card. If you have a core-facing line card, packets coming in are what? They are usually labeled. We don't need to do an IP lookup. So there we would, on a line card, so a core-facing line card, we'd only put of all the VRFs, but only the connected prefixes, not all the prefixes. Anyway, you don't need to worry about it. It's enabled by default, but it can save some space on the line card. Questions? Yes? V6, yes. Route target constraint is for MPLS VPN networks and for VPN v4 and v6 equally. In fact, remember the hack with the 4 communities? 2 were for v4 and 2 were for v6. What do you mean address family? Multicast. For multicast. So you mean for SAFI 2? I believe yes. Because there's also a different kind of multicast, MVPN. But yeah. Anything else? Yes?
A couple of slides back, you said that we did the per CE location. We might have big edge not working.
Yeah.
Didn't get right.
Yeah, I didn't explain why. So why is it not working? I really don't have time in this session to explain it, but there are a few things to it. But for example, with EI-BGP load balancing, when you hit a router, we also have to do an IP lookup after the MPLS lookup. And we might have a loop between the 2 egress PE routers temporarily. Well, it will not work temporarily. As long as the normal convergence has kicked in, let's say a few seconds later. Yes, you have the problem, okay. There you go, confirmation. Okay, so let me just round it up with the last section, which is OS enhancement. Again, can be quick here, we just did a few things for you. Another thing that came very cheaply for you guys, if you don't do any fancy layer 2 VPN stuff on an ASR 9K with the latest RSPs, what you could do if you want to store a lot of BGP prefixes is just enable this new profile that we have here with this command, and then you can go up to 2.5 million routes. Just mentioning it. Okay. Very important one, but only iOS XR, is the multi-instance BGP. Now, there's a couple of things here. In iOS XR, we are kind of limited on some of the boxes because they run on a 32-bit kernel, QNX, not NCS, that's 64-bit. And also not the virtual one, the ASR 9KV, that's 64-bit. If it's still running on 32-bit, as it is today, still, like the ASR 9K, like the CRS, then per process, you only have 32 bits, right? That's 4 GB of memory. That means BGP, one process, has 4 GB of memory. But there's overhead, so you end up with 2.5 GB of memory. That's not too much, right? One solution is multi-instance BGP. You just create multiple BGP processes, and each process has, again, a 2.5 GB of memory. Besides that, it could also be used for multiple autonomous system members. Yeah, already quite a few years, 3 or 4 years, something like that. iOS XR.
How many people are using it?
A few. I don't know. I don't know, but I know a few service providers using it. So you could do it for multiple AS, but here, again, you have divide and conquer multiple processes. The only thing which is kind of a caveat or restriction is each process needs to service different address families. So you could have process 1 do VPN-v4 and the other one IPv4. You cannot have both do IPv4. Yeah, no sharing of address families, exactly. So it will, you can have higher prefix scalability and more sessions. Be careful. Here, you do have from each process a different session, BGP session, to a non-multi-instance BGP speak, like an iOS box. But that's to be careful. And to wrap it up, we're on the hour. This is for your reference, but we did a lot of work, again, for you, sometimes just bits here and there or bytes here and there in the code, iOS and XR, over the last 5-6 years, to make things more scalable, right? The BGP uses less memory and less CPU. This is homework for you to read. So when is the boat not enough? Well, just for your reference, you have these commands to check when the convergence, how fast it is how much memory you are using, what is the CPU uses for iOS, iOS XR, and NXOS. I think we're on the hour. If you still have any questions, please come to me. I'll stick around a while. That's basically it. Thank you and enjoy the rest of the week.